We talked about livestock in the integrated management, but livestock waste is something that has to be managed very carefully as well, even for water quality. For example, places like the Chesapeake Bay, which host on the eastern shore massive poultry farms and pig farms, actually, and of course all the agriculture with livestock, release enormous amounts of nutrients into the water, which actually favor harmful algal blooms, which create other problems. Plus, with the warming, it's also becoming harder to sequester nutrients anyways, so the deoxygenation and harmful algal blooms together can cause massive fish kills and other problems. So livestock waste can be used in anaerobic digesters to produce methane. We have already seen that before, but the digestate that is left behind has lots of organic carbon and high nutrients that must be composted, and the remaining parts have to be monitored for nitrogen emissions and polluting chemicals that get released potentially into the water bodies or soak into the groundwater. So this is one schematic from this source showing input waste management from cattle and pig manure. We have talked about feeding cattle, for example, seaweeds to reduce their methane belching. Conversion technologies like biodigesters can produce biogas, can be large scale or small scale, and the outputs of flows include biomethane and biogas for heat and power, vehicle fuel like biofertilizer, and also biofertilizer application to land, which work as amendment also, for example, changing soil properties. This is to look again at the mitigation and the bending the curve that we have talked about. So this is showing a slightly different thing here. Instead of emissions, it is showing the ratio of net anthropogenic emissions, which include the sinks and sources, and then the net natural sinks like land, forest, ocean, etc. Projecting from the historic period of 1950 to projections out to 2100, and on this side it shows the resulting warming with a equilibrium climate sensitivity of 3 degrees centigrade per doubling of CO2. We haven't talked much about climate sensitivity, but basically it's a calculation which looks at what level of warming the climate system accomplishes or achieves if we ramp up the carbon dioxide concentration to double its value at any point and leave it there forever. So there will be a transient response like we are in now. We have been increasing CO2 since industrial revolution, and we are still increasing it, so we are in a transient climate response. But if we shut off the CO2 emissions completely, the warming will continue for a while. So that's what we mean. Okay, so the various scenarios here, business as usual, and different kinds of fossil fuel choices. Business as usual, renewable energy as a low option, low fraction of the total portfolio. Renewable energy still at low, but you add some level of carbon capture and sequestration, so you bend the curve down to here, and going to renewable energy high brings you down here. If you add carbon capture and sequestration, you can come way down here in terms of your warming target in the range of 2 to 2.5. So you can see that each one has a range, because obviously these are scenarios. There are scenario uncertainties, there are technology assumptions, and so on and so forth. So these are the awesome ones that we want, right? To bring the warming down to 1.5 degrees or less, you will need very high renewable energy contribution plus full carbon capture and sequestration, none of this half business. Then you have the opportunity to start bending the curve very seriously. Of course, the story is that we are still on the business as usual scenario, so long way to go. Land-based solutions then include reduced or no tillage. After harvesting, the tillage tends to disturb the soil, makes it easier for emissions to increase and loss of carbon as well. They're related to each other. Soil moisture and soil carbon have a positive feedback. For example, increased soil moisture increases soil carbon sink or storage or persistence. Improved grazing regimes. Grazing can actually harm the topsoil quite a bit and not good, especially concentrated persistent grazing in these industrial farms. Fire management, again a controversial topic in terms of whether it actually helps or not. Removing the fuel created by dried up vegetation. There are papers that human beings have been doing this already anyway, so the question is whether wildfires are increasing because of that or not. Use of cover crops, we talked about legumes, use of plant species with high root allocation, so the biomass and the hydrocarbon sequestration can be increased. Conversion from annual to perennial crops. Annual crops have a cycle that requires sowing and harvesting, which affects soil quality, soil health, and soil emissions because there is tillage involved often. Crop rotation involving perennials, agroforestry, which mixes trees with agriculture, which is shown to reduce evaporative losses, increase soil carbon, increase soil moisture persistence, enhance drought resilience, and so on and so forth, and often provide non-rainy season income and create also non-farm sector jobs. If you make the right choice of trees, rainy season in India could be just 4 months for most of the country, and then 8 months you have to provide some employment and source of income, and there are lots of socioeconomic problems associated with that period. Wetland restoration. Wetlands are high carbon sequestration places. Fertilization obviously has to be managed with natural fertilizers, reduced industrial fertilizers, or precision application, and so on. Irrigation is a big problem. Precision irrigation can help. Organic matter amendment, so using practices like no tillage and livestock management grazing, one can do soil property improvements to increase carbon content, etc. Okay, so here is a table from the book showing potential global soil carbon sequestration with improved agricultural land management. So these are the management options. Biochar, I will show what that means. Nutrient tillage irrigation we talked about. Grazing, combined potential excluding biochar, combined potential including biochar. Land use types, they can work for all land use types, only for crops of course. Rangeland, where livestock is the main production, and these can be combined for all land use types. So mean sequestration potential, the maximum range and the minimum range up here. So you can see that the combined potential is up down here at almost 2 petagrams carbon per year, and the high range it can reach almost up to 3. Pretty small number compared to the total emissions from humans, but remember the co-benefits that go with these. That's always very critical, because those kinds of costs are not accounted for in just monitoring carbon. So managing soil organic matter is key to air and water quality. So using cover crops, reduced tillage, organic matter management, soil amendments, increasing water holding capacity, emitting fewer pollutants, less dust, of course. If you have increased water, you have less dust. So actions here: prescribed grazing, high biomass rotation, manure management, soil organisms, we need to protect them, soil structure, infiltration and nutrients, infiltration of water and nutrients, less sediment into the water bodies, drought and disease resistance. So Managing these improves soil health and improves soil and water quality and agricultural productivity. Beautiful, beautiful, right? Obviously, scalable policies, mix of land-based, market-based policies are needed also to ensure food security, water security, health security, and so on.